Okay, the last problem we're going to look at in section 5.2 is number 29, and here we're told, actually I'm distilling what is in the original statement of the problem. It's fairly complicated, and so I'm trying to get to fewer words, and I hope that makes it a little bit more understandable. In summary, in a certain arid part of the United States, there's enough water for a good wheat crop in about 65% of the year. 65% of all years. Farmer Z expects that there will be a good crop 4 out of the next 8 years, and we're asked to compute the probability that there will in fact be 6 good years out of the next 8 if what he believes is true. Now, by my way of thinking about it, if we didn't have this sentence here, I would probably not interpret it. I would probably not interpret the question the way that this is stated at all. It kind of sounds to me like, in general, there's a 65% chance of a good crop. Farmer Z thinks there's 4 out of 8. That's a 50% chance of a good crop. So what's the probability that 6 out of the following 8 will be good crop years? That wasn't apparently what was intended at all. We're supposed to continue on with this assumption that overall a 65% chance of a good crop year, but throw in as an assumption now, when we're asking for the probability that R is at least 6, let's go ahead and assume that we already know that 4 out of the following 8 will be good crop years. Now, if you accept that interpretation, then what we have is a situation where you're asking for the probability that one event occurs given that another event occurs. This vertical line is read as given. Let's zoom down then to part C, and the text gave us a little more information. They instructed us to do a certain kind of review, and then they just basically put the review there for us. So you can look this up in section 4.2 if you'd like more detail, but this is the essence of the review. The probability that A occurs given that we know B occurs is the probability that both A and B occur divided by the probability that B occurs. So if we take this formula right here and we take A to be the event R is at least 6 and B to be the event that R is at least 4, then you can translate this to this right here. There was a little problem with the typing, but it's been fixed. One other thing I want to mention, and it's a little bit unclear why it was stated this way in the textbook. We really got used to this kind of notation: R is at least 6, R is at least 4, and then suddenly in this problem that's reversed, so 6 is at least R. Well, 6 is less than or equal to R is the same as R is greater than or equal to 6. So that one, R greater than or equal to 6 and 6 less than or equal to R, are completely equivalent. They're just turned around backwards. I don't know why. Just adding yet another wrinkle in our the work that we have to do for this problem. So we are trying to answer this question: what's the probability that R is at least 6 given that it's at least 4? Well, using our formula here, it's the probability that it's at least 6 and that R is at least 4 divided by the probability that R is at least 4. Well, that is already in the form we want it, but we examine this a little bit. Suppose we have 6 successes. Well, then we automatically have 4 successes, right? So if you have 6 and 4 successes, then, or I should say it this way, if you have at least 6 successes and at least 4 successes, that can be simplified to simply saying you have at least 6 successes. So that translates to this, and that is the way this part up here is going to be worked. So let's dig into that and do that calculation. With all of that background, we now know that what we're being asked to do is this. We are to assume the probability of success in a single year is 0.65. We're working with an 8-year span, so we have 8 trials, and we are asked this conditional probability: what's the probability that R is at least 6 given that R is at least 4? Well, According to the review in Part C, that's the probability that R is at least 6 divided by the probability that R is at least 4. Now, it would be great to just type this into the calculator directly, but we can't. These are greater than or equal to inequalities, and we have the binomial PDF, which would get us an equality, and we have a binomial CDF that will get us a less than or equal to. Well, we do these by complements then. That's 1 minus the probability. Okay, so we got 8 years. If R is at least 6, that means 6, 7, or 8. So what's the opposite of 6, 7, or 8? Well, 5 or fewer. So R less than or equal to 5 is the complement of R is at least 6. And in the same way, if it's not at least 4, then R is less than or equal to 3. Okay, now you can set this up on your calculator and do it all in one big calculation. I'm not going to do it that way for this example, mostly because, well, entirely because it's hard to follow on the screen. But you can manage this without any intermediate values. So 1 minus binomial CDF, we have 8 trials, probability of success is 0.65, and we want 5 or fewer successes here. Same thing here. 8.65, and now we switch to 3. And now I'm going to get these two numbers off of the calculator, and then we'll do the arithmetic after we have those values. So second distribution, scroll down to B, binomial CDF. I have 8 trials. Probability of success is 0.65. The first one I'm interested in here is 5 or fewer successes. So paste that in and compute. That is 0.572186. And now we want to look up the corresponding probability with 3 or fewer successes. So the entry key will do us some good. Change that to 5 to a 3. And this one is 1060909. So there's the arithmetic we need to do. So 1 minus 0.572186 is 0.427814, and in the denominator 1 minus 0.1060909 is 0.8939091. And then we can compute the ratio, and we get 0.47859. So we get about a 47.9% probability that there will be at least 6 good years if we know in advance that there will be at least 4 good years, under the overall assumption that the probability of a good year is 65%. Now that completes part A of this problem, and if that satisfies you, well, then you're done. Let me just mention, though, that you can avoid a lot of this typing and retyping values just by using your calculator a little bit more efficiently. So what I'm going to do is clear this out, and I'm going to go back and type in this fraction right here without any intermediate steps. The trick is that you want to use some parentheses. So I'm going to have parentheses 1 minus second distribution, go down to option B, binomial CDF. I have 8 trials, 65%. First one of interest was 5 there. Paste that in, close the parenthesis, divide by, and now I'm going to have another set of parentheses that have this denominator in it. So that is 1 minus second distribution binomial CDF, and everything is the same except I have 3 here. And that gives me my 0.478, etc., all in one calculation. The reason I did it this way at the beginning was just to make it easier to follow, but if you are trying to move along quickly, then build a skill with a calculator. You'll be better off doing it all in one fell swoop. Okay, that takes care then of part A, and really it takes care of part C as well. It just to ask us to take note of this, and there's really nothing to do for part C. You just read it. For part B, on the other hand, it asks us to list 3 areas besides agriculture where conditional binomial probabilities can be applied. Well, the truth is, any place you could be using binomial probabilities, you could be asking questions about conditional binomial probabilities. So for instance, I'm going to flip a coin 10 times. What's the probability that at least 6 times I'll get a head? Well, that would be this kind of a question. What's the probability that R is at least 6? Well, suppose now that by some magical process you happen to know that when I flip the coin 10 times, that you already know for some reason that I'm going to get at least 4 of those are going to be heads. So then you could say, well, what's the probability that I'll get at least 6 heads if I know in advance that I'll get at least 4? Well, that's a conditional binomial probability, and this would be probability that R is at least 6 divided by the probability that R is at least 4, just as it was before. And if we were going to do that for 10 flips of a coin, rather than 8 crop years, we'd still be doing a complement and be taking a ratio. So any place that you can use binomial probabilities, you can also use conditional binomial probabilities. And flip of a coin would be one answer. How about in healthcare? Maybe you're looking at patient records. You restrict yourself. Well, how about this? You restrict yourself to patients who have had already at least 1 heart attack. What's the probability that that patient is going to have at least 2 heart attacks? Well, it's the probability that you'll find at least 2 heart attacks, given the fact you are restricting yourself to the records of those who had at least 1. You could look at this, say, in the stock market. What's the probability that in the next 8 years we'll make a profit? If the probability of profit is 65% in any given year, but by some reason we know, or at least that we're going to assume, that over the next 8 years we will have 4 profitable years. Well, if we know that we're going to have 4 profitable years, what's the probability that we'll get at least 6? It'd be exactly this kind of a calculation. So any place you can use binomial probabilities, you can also use conditional binomial probabilities, and so in a certain way, this is not a terribly insightful question. Just think of places where you could find binomial distributions, and there are your answers. Okay, that takes care of number 29 in section 5.2, and in fact takes care of all of the problems that we want to review in this homework help.